Okay, so I will measure these luminosity distances then in cosmology. Sorry, supernova type 1a cosmology. Before I move on to this, let me show you that plot of the non-Gaussian distributions I wanted to share. This is not cosmology, but I just want you to be aware of what happens when things get nasty. This is a problem I started getting involved in 2005. This is about determining supersymmetric parameters from... You lost the image? That's strange. Everything is fine here. Can you see me? Okay. Let's restart the Hangout. Now? Can you see the screen? No? Ah. Well, let's restart the Hangout. Okay? Hello? Can you see me? Can you see the screen? Good. So I just wanted to say this is a problem I started to work on in 2005, and I thought, well, this is about determining supersymmetric parameters using a combination of data from now the LHC and then direct matter detection and so on and so forth. It doesn't really matter. The point is that I thought, well, I'm going to apply some of those very successful MCMC techniques that we've been using in cosmology for many years to this problem and do it properly and crack it. Now, 10 years later, I'm still working on this problem because it's so hard for technical reasons that we don't have time to go, and physical reasons as well. But just have a look at this at this results here. This is essentially a 4 parameters model. So this is not a large dimensional space. And what you see here are posterior distributions for 2 parameters. If you look, for example, at just the field contours, you will see here is a distribution for uniform priors on the parameter. Here is a posterior distribution for log priors in the parameters, and you will see that these 2 regions look approximately the same, but the log priors, say priors that are uniform in the log of the parameters, they find another high posterior density region down here, which is completely missed in this flat prior case. And then if you do profile likelihood analysis, which is what particle physicists would do, you get something, again, completely different. Look at what the profile likelihood contours look like. Much tighter than the Bayesian posterior. There's nothing up here in the profile likelihood sense. So, and this is work that we've done very recently, state of the art, using all the data we can grab. All I want to say is that in cases such as this, where there's something really difficult about the parameter, your prior assumptions might matter, as they might do in the Bayesian analysis, but equally, whether you do marginalization or whether you do profiling really changes drastically. There's your scientific inference. I mean, if you look at the profile likelihood result and you forget the Bayesian, you conclude that the upgrade of the LHC that's going to restart next year is going for sure to test this model, because this line here tells you what is the current limit of the LHC, and when it upgrades to 14 TeV center of mass energy, it's going to cover this region for sure, and so you're done. In the Bayesian sense, this is very much not the case. In fact, your posterior distribution tells you that most of the posterior mass is out here in a region that the LHC is not going to be able to see. And I still don't know what to do about this problem in terms of which of those results to believe. So anyhow, that's just an example of things that are very non-Gaussian and very nasty. Okay, back to supernovae. Okay, so the plan is simple. We want to use the standard candles and use this relationship here. Distance modulus at redshift z, which depends on cosmological parameters, is given by the difference between the observed magnitude and the absolute magnitude, which we don't know, but we know it's a constant if the supernovae are all the same. The type 1As are all the same. Z is observed, at least if we have spectroscopic data. We can just measure the Z to very high accuracy, 10 to the minus 2, 10 to the minus 3 precision. So all that remains to do is to infer the omegas, cosmological parameters. But, so, remember the Hubble law says that velocity, the reflection velocity, is proportional to h0 times the distance. So, if we log that relationship, we get that log v is proportional to log h0 times log distance, which means that log v is proportional to a constant times a slope times mu, because log d is nothing else but the distance modulus up to the constant in front. So in other words, if you plot, at least this is true for nearby objects, sufficiently nearby objects. We know that for larger distances, the Hubble law here needs to be modified according to the proper angular distance or the most distance. But this is true for relatively nearby objects with redshifts much smaller than 1. Let's say redshift much smaller than actually 0.1. So what this is saying is that if we plot log v, which for those objects is just c times z, so z we know, c we know, and we can compute v. If we plot log v versus mu, we should get a straight line. Like this. Right? Unfortunately, this is not the case. Let's look at this plot here. So this is exactly this plot for nearby objects. So log v versus the distance modulus, and if everything is fine, you'd expect those objects to line up along this line. They kind of do, but not well enough. There's a large portion that makes them not good enough standard candles. If you look at this dispersion carefully, you will find that this dispersion is about, on average, the standard deviation is about 0.5 magnitudes, which is not nearly enough to make them standard candles for cosmological use. Please remember that the typical distance between different cosmological models is about 0.5 to 0.2 magnitudes. So if those objects have a dispersion of 0.4 magnitudes, you're done. There's nothing, you can't use them as standard candles. However, they're not standard candles, but they are, it turns out, standardizable candles. You can use a statistical procedure, which I'm going to describe, to make them more standard. And that is what happens in this plot here. After this correction procedure, you can see that now is the dispersion around the linear relationship is much reduced to about 0.1 or 0.12 magnitudes. And that makes them good enough standard candles to use. Okay? So the point is that they are not good enough on their own, but they can be made into standard candles, statistically speaking. So how do we get them standard enough? That is a statistical problem. That's why I'm bringing this up. There are two key observations to this. So what we observe of supernovae is not just their magnitude. We observe the flux of those objects, the function of time in multiple colors, multiple broadband transmitters for the astronomers. Here is an example of the data. Okay? Here is an example of supernova type 1a observation from the SMLS survey. And what you see is that this is time on this axis, so that's days. And you can see the flux function of time in 4 different color bands, G, R, I, Z. And you can see that what happens is a supernova goes off, becomes bright, and it fades again over a period which is of a time scale of maybe 10 or 15 days. It fades and then it disappears back to it fades away. And you can see that depending on the color, the maximum is slightly different, the shape of the light curve is different. So this is what we observe. And the question is, how do we use this to infer distances? And there's one key observation that people have made. And what they've observed is the following. Let's look at this plot. Here's a plot of light curves in the B band. That's a band that's centered around 436 nanometers for the astronomers in the room. And on the y-axis, so here's time again, normalized, right, at 0 is traditional B band max. So that's the maximum luminosity of the object. And this is absolute magnitude, absolute B band magnitude. This is the absolute magnitude which has been obtained by taking the apparent magnitude and converting it into an absolute magnitude because the distance to those objects is known. Those are near enough supernovae that we can measure their distances using other methods, from Cepheids to the Fisher relation, whatnot, etc. It doesn't matter. So we know the absolute magnitude of this object, and as you can see, at B band max, the version of this absolute magnitude is huge. Is over 1 magnitude. Those are not standard candles at all, right? But you also observe another key thing in this plot. Which is, remember, in this plot, this is absolute magnitude. So at the top end, those are brighter objects. At the bottom end, those are less bright objects, fainter objects. So what you observe is that the brighter objects, they decay more slowly. It takes them longer to fade away, while the fainter objects, they are more quick to fade away. Okay? So this is the key observation that was made. I think originally the seminal paper goes back to Phillips, 1993. In other words, what's been observed is that reasons that are not physically well understood yet. The brighter objects are slower to fade, and the intrinsically fainter objects are faster to fade. And so because we observe the light curve evolution, and therefore we get the shape of the light curves, and we can work out the time it takes for them to fade away, we can use this fact, correct the curves, and use this correlation, empirical correlation between the time it takes for them to fade away and their intrinsic luminosity to bring them all back in line and obtain standard enough candles and standardize them using this observed property they have. So here's how it works. I just told you in the sketch, brighter are slower decaying. And by slower decaying, one of the parameters that's used to parameterize this decay is this delta M15 quantity. Is the magnitude by which they faded away 15 days after B band max. So brighter means slower decay. If delta M15 is smaller because they fade away less in a given time, in 15 days. And vice versa, I can even use a different color here. And vice versa, here, fainter objects, faster decline, larger delta M15. So in other words, we have this empirical correlation here, which is called the Phillips relation. The Phillips relation says that there's a correlation between V-band maximum intrinsic magnitude and delta M15. So the brighter objects are the ones that decay slowly. The fainter objects are, the fainter objects are the ones that faster decay. So that's qualitatively what it is, and this is what the data look like. Here's an example. Down here, if you can see, look at this plot. This is the original plot from Phillips, and it's plotting V-band max and delta M15. You can see that there's a clear correlation. V-band, V-band, I-band. It becomes less clear in the I-band, but it's very clear with the V-band. Okay. And so, right, so if you know that, you can use this fact to empirically correct the magnitude of the supernovae, exploiting the light shape. So now there's another such correlation that's being pointed out slightly later, and one of the papers that did that first is the color correlation. Here you see again, this is a paper by Rees Press and Houston in 1996. You can see again, this is intrinsic magnitude in the band for a number of objects nearby. You can see the same thing again. The brighter objects are slower to decline. The fainter object decline more quickly. But what they also did, they look at the color of the object. They looked at the excess V minus V color, excess compared to the mean. And what they observed is that in the early days, especially in the early days, in the raising part of the light curve, what they observed is that dimmer objects, which are the squares, dimmer objects also have a redder color, brighter objects. There appears to be also a correlation between the intrinsic color of the objects, as measured by this quantity here, and their magnitude. Okay. So there are two effects here. Let me see if I have a plot of that. I don't have a plot of this color. Let's see. I don't have a plot of that. But it's analogous to the decline time magnitude. There's an observed empirical correlation between the intrinsic color and the intrinsic magnitude of the objects. So, what we end up with is a picture where we have intrinsically fainter supernovae that are redder and fast decliners, and intrinsically brighter supernovae that are bluer and slow decliners. And so the point is that we can observe how long it takes for them to fade away by measuring the shape of the light curve. We can observe the color of the light curve by looking at it in different pass bands, and we can use these two facts to statistically correct the magnitude to compensate for this correlation effectively and standardize these objects. And that's a statistical problem. Now there is lots of astrophysical messiness that we deal with if you want to do this properly. I don't want to go into too many details because it becomes very astrophysics, and you have to worry a lot about absorption by dust. Because, in fact, what all you observe is the flux of the objects on the sky, and they will appear dim to you, There are three reasons why they can be dim. They can be dim because they are distant, and that's a cosmological effect, which in turn is controlled by the cosmological parameters. As we know, the luminosity distance is controlled by the cosmological parameters. They can appear dim because they are obscured by dust. And this is a problem that is very important because dust will absorb light and also redden the color of the light, and this will confound your observations. Or they can be dimmer because they're intrinsically dimmer. There's intrinsic variability to small objects. That's something we don't know. So really, the statistical problem is how do we disentangle these three things, and can we do so in such a way that we can confidently reconstruct the part that we're interested in, namely cosmology. Okay, so it turns out that the most important part that you need to worry about is dust. I just want to mention what I believe to be the best approach, the state of the art in the field. This is the approach taken by Casey Mandel and collaborators, Kirchner and Patrick Kelly, etc., the Harvard group. I don't have the time to go into the details of this highly sophisticated approach. I just want to flag it as the art of analysis, in my opinion. What Casey does in a sophisticated way models the dust and the reddening brought about by the dust in post galaxy explicitly via a sophisticated Bayesian hierarchical model, and it does so with partial pooling and a very sophisticated model that I can't go into today. Although if you're interested in supernova type 1a cosmology, I definitely encourage you to look up Mandel et al. 2000 and subsequent works. So this is state of the art. Too complicated for us to talk about today, but look it up. What the two other mainstream approaches, which have been used for 10 plus years, and I think those two approaches are actually now showing the trend. They are now at the point where they're not sophisticated enough to deal with the complexity of the analysis that we're facing now that the supernova sample is in the several hundreds, will be several thousands in the future. Systematic effects and data modeling effects of the kind that Mandel et al. Are approaching are limiting the ability of understanding supernovae, and the old-fashioned methods are not enough. The so-called SOT2 approach is to fit the light curves of the supernovae with a template-based method. So what the SOT2 does effectively is something like this: to take the observed data points and fit them with a model of the light curve shape and color that's learned from a nearby training sample of supernovae. Now you need to fit those observations because obviously from a data point of view, this is a complicated problem. You've got uneven temporal sampling. You don't have equally spaced data points simply because you can't observe those objects when and how you like. You have missing data. You've got data points where you have only one color but not the other. You've got regions, for example, where you have large chunks of time where you don't have data points. You've got where the nominal flux is negative, which is due to background subtraction problems. So it's a complicated mess. If you want to do this properly, and Mandel et al. Do this properly, you have to deal with missing data, imputation, correlation, etc., etc. So it's a very interesting statistical problem. But the SOT approach is relatively more straightforward. Just fit those data using a template-based approach, where the templates are based on locally observed supernovae whose distance is known independently. You know what their intrinsic magnitude and like. So this is what people have been doing for a long time. And so what the SOT2 does, they lump together everything in terms of color and stretch correction. The stretch correction being the correction for the fact of the different time scale of decline in the light curve, they lump everything together in just two parameters. One parameter is the color correction parameter, which is called C. Oops. C being the difference in color between the B minus B excess at maximum minus the B minus B average color. So it's a color offset with respect to the average color at maximum in the B band. It's also part of the color correction that's time independent. And then there's another parameter which is called X1, which is a so-called stretch parameter. You can think of X1 as a version of the delta M15 parameter, telling you whether the supernova is a fast or slow decline. It's called stretch parameter because it stretches the time axis of the light curves that fit to the template, to the average template. Okay, so then, with all of this, the statistical problem in this relatively simplified approach boils down to this. So here we have the distance modulus, the B band, given by the B band max, observed B band max, minus the B band intrinsic magnitude, capital M. And then we correct the intrinsic magnitude linearly by putting in the correction for the observed correlations I was telling you about. One is a stretch correction, and one is a color correction. Those are linear in X, stretch parameter, and linear in C, color parameter. The strength of each correction is determined by two global parameters which are unknown and need to be learned from the data. And those are alpha, the stretch correction strength parameter, and beta, the color correction parameter. You can relate beta to the reddening law, the average reddening law, due to dust. I won't do it here because it would get us into the details of dust, host galaxies, blah, blah, blah. Very interesting from a statistical perspective, but not from a statistical perspective. Okay, so the statistical problem is this. What our salt to light curve fits will give us is quote-unquote summary statistics of the observed data. And the summary statistics, the data that we have are this here, the observed B band max magnitude, the stretch, and the color. Those are observed quantities, and there's a correlation covariance matrix between them. M is a global unknown parameter, is the absolute magnitude of the supernova, which we assume is the same for all of them, up to variability term that can also be estimated from the data. Alpha and beta are also unknown and have to be estimated from the data. And the distance modulus is the quantity that depends on the cosmological parameters of interest. That is what we want to infer. And that's our problem. How do we do this problem, this statistical problem? Questions? Okay, so let me tell you a little bit what people have been doing for years and why I think it isn't good enough, and then I'll tell you what is the Bayesian solution to this problem. Or at least I'll sketch the solution. So the standard approach is to say, so the standard approach is to say, fine, we're going to write down a chi-squared. Not for any good reason, but just because that's the simplest thing to do, and we'll assume things are just Gaussian, because we don't know what else to do, basically. And so the chi-square is, in the standard approach, is a sum over I, where I denotes the supernova that you're looking at, of the distance modulus to the supernova at redshift Zi, which is a measured quantity, which is a function of the cosmological parameters, as we know, minus the observed value of the distance modulus, which is made of the observed B band value with a hat coming out of the sort 2 minus the intrinsic magnitude plus the stretching color correction terms. Yeah. Essentially, it's theory minus observation in some sense. And then we'll assign to it an error term given by sigma square thick. This represents the intrinsic, that's to say the residual scatter, the intrinsic dispersion of M. That's to say the intrinsic variability of the supernovae after corrections, which is unknown. We don't know what that is. We know that these objects are not all the same and that there will be some residual intrinsic variability that needs to be activated because we know they're not all identical. And then in quadrature, we add in the sigma square from the fit, which is just the error terms associated with the observed values coming out of the fault 2 fits with error propagation, standard error propagations here. So that's the error in the magnitude, the error in the stretch parameter, and the error in the color correction. Okay, and then what people do, they do some sort of fit, which is not even an MCMC fit, for the unknown parameters in this expression, which are the cosmological parameters we care about, intrinsic magnitude, if you care to know what that is, alpha and beta, and sigma intrinsic as well, which is also an unknown parameter. There are several statistical problems in this. The first statistical problem is that what people do, they just inflate sigma intrinsic by hand until they get a chi-square per degree of freedom of 1. In other words, they make the error as large as it needs to be for their fit to be good, as measured by the chi-square per degree of freedom criterion. That's not a good idea, because your fit is then, by construction, a good fit. You have made the error big enough so that chi-square per degree of freedom is 1, so that prevents any meaningful model criticism. It prevents any model checking, for example, in the way of computing p-values for your method, if you're so inclined. I'll tell you in the next hour that you shouldn't be inclined to use p-values anyhow, but if you must, of course your p-values would be good because you inflated the fit to be good. So that's not a good idea. But equally, this form of the likelihood is simply not justified. It's something that looks like a Gaussian likelihood, but it shouldn't be, because if you notice, these parameters, alpha and beta, they appear here in the numerator of the likelihood, but they also appear in the sigma square fit error propagation formula. You see that sigma, alpha, and beta are unknown parameters that also appear in the variance of your expression. That means that chi-square, or a Gaussian likelihood, is not the correct distribution. Those two quantities are not only here. This is not a Gaussian harmonic alpha and beta. It's a problem of estimating the variance as well, not Gaussian. This likelihood here is incorrectly normalized. The log likelihood chi-square expression here assumes that the normalization constant is independent of the parameter, but it's not, because this is a variance measurement. Parameters that you try to estimate also appear in the normalization term in front. If you add this term in by trying to fix it, makes things worse. It gives you a huge bias determination of beta, which is a well-known parameter, well-known problem. People are trying to avoid by ad hoc dropping this normalization term. We will see later where this comes from. And also because the likelihood form is unjustified and incorrect, you can't use MCMC techniques with this likelihood, because if you do it, you would only end up with a bias completely wrong posterior, not because the MCMC is wrong, but because the likelihood is wrong. So, bottom line is that what you need is a principled Bayesian approach to this likelihood and to the entire inference problem, and to make this work. And this is what my student Marisa March and our collaborators and myself have done a couple of years back. I just want to sketch what the solution is, which involves the use of principled Bayesian hierarchical modeling. Okay. So fundamentally, what we're trying to do here is nothing else but linear regression, the presence of measurement errors on both the dependent and independent variable, and intrinsic scattering the relationship. Now, I put down a couple of references here, but the reference for this is Kelly 2007. Now, I'm slightly uncomfortable in talking about, linear models. I don't know if Tom is in the room, but he is, talking about hierarchical Bayesian models. When Tom is in the room, he's one of the experts in this. So I'll try to sketch them here with apologies to Tom and the other experts in the room, because it's going to be very, very sketchy. But certainly, Brandon Kelly's paper from 2007 really is a very good paper for astronomers, which has got all the statistics right. It's got much more detail than I can cover here. I refer you to it for more detail. But so if you look at this relationship here, what this relationship here is effectively a linear model, or almost linear model. Nu I is not quite linear in the parameters, but everything on the right-hand side is linear in the parameters that we're trying to infer. And it's fully analogous, correct this, analogous to a linear model here with a hierarchical structure. So the linear model, I remind you about the hierarchical linear model. So here we have yi is given by b plus a xi. And now the xi themselves, the independent variables, are drawn from their own distribution, p of xi, which itself is controlled by the parameter psi. And here, for convenience, I'm choosing this distribution to be Gaussian with unknown mean x star and unknown variance rx. So we call this the population distribution of the xi's. This xi here is the latent value, is the unknown, unobserved true value of the xi's, which we do not observe. What we do observe is the xi hat. The error is the value of x with observational noise. If we know the xi, condition on the xi, then we know what the yi is, what the response variable is. And that's, again, a Gaussian distribution in the presence of Gaussian errors around the regression relationship, b plus a xi, with intrinsic dispersion, sigma squared. And then finally, we have the observed value of xi and yi. If I have the latent values of xi and yi, is again a Gaussian controlled by covariance matrix sigma squared, which is the one denoting measurement error. So that's in a nutshell the hierarchical model structure. Okay. Let me sketch it to you again, just to make it very clear, I hope, and make contact with stuff that Tom already told you. So here we have our model, our data, x and y. And what we have the xi's here are measured. How am I going to do this? So we have an intrinsic latent value for the x's, which is there. And we have an intrinsic latent value for the y's. Now, there is a linear relationship between the two. Y equals a plus bx. But this is not an exact relationship. In other words, even at the latent level, even before we add measurement noise, the y's are not exactly lying on top of the regression line. They lie around it with intrinsic scatter given by sigma squared. The intrinsic variability here is sigma squared, which is one of the parameters that we estimate. We don't know what the intrinsic variability is. So then we add measurement noise. And the measurement noise, that does is it further scatters them in the x direction and in the y direction. So this point here will be scattered, say, this location, and this point is scattering this location, this, And then we have measurement errors on both of them. And that's our model here. Right, and so the principal Bayesian solution is to model this as a hierarchical model of the kind that I just mentioned. Here I want to go back to the Kelly paper just to make a point to show you that the important question here is the ratio between the intrinsic population variability of the axis and the measurement error scale. In other words, this plot shows the x and y location at latent level. So those are the blue points in my sketch before. That's the location of the x and y's before I add noise. And you can see they cluster around the regression line, but there is variability in them. So in this case here, so this box there is this box here. In this case, the measurement noise is relatively small compared to the scale variability of the axis. So in this case, the measurement error doesn't really make a huge difference. And so you can fit this kind of data with a linear regression. You can do least square regression, chi-square, whatever you like. In this case, you're going to get almost the right solution if you don't use a proper Bayesian approach. But in the case where the measurement error is large, of the same order compared with the variability of the x-axis, things get nasty. What happens is that your latent points get preferentially scattered up by noise, then scattered down. In other words, if I observe the point here, it's much more likely that this point here has been scattered up by an upward fluctuation of the noise, so it comes truly from the latent value of x down here, then it is probable that it comes from out here coming down, simply because at the latent level there is less axis out here. The population dies out. So this is what astronomers call Malmquist bias. And they call it a bias because the chi-squared or maximum likelihood or least square approach is not accounted for because the distribution of axis at latent level is ignored. And so you need to correct for that. If you don't correct for that, you're going to get very biased estimates. Most importantly, of the slope of the regression line. But if you do the things properly in the Bayesian approach, you don't need to account for it because it's no longer a bias. It becomes simply an effect in the population, in the hierarchical structure of the model, and it's accounted for automatically. That's why Bayesian methods are so much better in this case. So here's an example. Simulation of exactly this case. Here we have simulated data where you see the observed and the observed x and y in the case where the error, scale of the measurement error is relatively small compared to the scale of x variability. And you can fit this linear model both in the chi-square sense and in the Bayesian sense, and you can marginalize or profile down to the slope, to the A. And so this chi-square fit is done using a chi-square likelihood of the type I showed you before. This is the wrong likelihood, as I told you before, for all the reasons I explained. The Bayesian fit is done using the full hierarchical model and a complete data likelihood that looks nothing like chi-square likelihood. And the extraordinary thing is that if you compare the two solutions, in this case here, even though the likelihood is completely different, the 1D marginal posterior for the slope or the one-dimensional profile likelihood for the chi-square approach are almost identical. Yet the right answer, the truth is 1, and you get the right answer up to realization noise. In the two cases, extraordinary, exactly the same result in this case. But when the errors becomes larger, then the two results differ. And the chi-square result here in black is biased with respect to truth, while the Bayesian result is less biased and it's closer to the truth. despite the fact that it's got larger variability, larger uncertainty. So the Bayesian margin of posterior is broader but less biased than the profile likelihood because it accounts correctly for the error structure in our model. So then, what we have done, we've applied these ideas to the supernovae case. I don't have time to go through the what can I say? I will just say this. Do I have a plot? Let me see if I have a nice plot. No, I don't have a plot, but I just want to say that what we've done, we have applied this Bayesian hierarchical model to the supernova case, to the supernova data, and compared with the usual way of doing things. And we've compared on 100 simulated realization of the data, and we've compared the performance of the Bayesian hierarchical model to the chi-squared approach. We've computed the bias for each cases and the mean square error, which is the bias square plus the variance. And we've also compared the coverage of the credible intervals and the confidence intervals that we get from the chi-square. So what we observed for the various parameters of interest, we observed that the Bayesian approach gives you better coverage, if you care about coverage, not perfect coverage in blue with respect to the chi-square, but better coverage than an alleged frequency procedure. It reduces bias by a factor of 2 to 3, and it reduces mean square error by a factor of 1.5 to 3 for all parameters. So overall, here we have a principled approach that performs so much better on all indicators than the standard approach. The cosmology that results from those fits is omega lambda, omega matter plane, not drastically different from the chi-square approach. A reflection of the fact that those errors are fairly large, so the true power of this method is not yet evident in this data set, which encompasses 288 supernovae. But we can also obtain fully marginalized posterior of all the parameters of interest and the nuisance parameters, the alpha and beta parameters, and also the intrinsic magnitude. So that's the central dispersion in the magnitude of supernovae post-Phillips corrections, which is found to be the marginal posterior with 0.13 plus or minus 0.01 magnitudes. So the point is that this can be done, supernova cosmology from a principal approach can be done in a very effective way. And finally, I also want to conclude this part again by giving a little bit more detail about the Mandel approach, which I think Tom already mentioned. This is a much more sophisticated hierarchical model where you have population level distribution for dust parameters, current parameters with appropriate priors, realizations of each of them for each one of the supernovae. This gets converted into the apparent light curve, and this into the observed light curve, and all of that gets fit in the context of a highly sophisticated hierarchical model. And this allows case and collaborators to do things like this. For example, reconstruct function parameter and a reddening law for each supernova on an individual basis. For example, you can see here two cases for AV versus RV for the aficionados. And it allows them to do things, to investigate each one of the supernovae individual object by object, reconstruct their dust absorption properties and distance modulus individually. But also it allows them to look at population level analysis of correlations, for example, between delta M15 and the peak brightness in the various bands. What you can see here, for example, from this population level plot, is the correlation matrix across all of the supernovae, the different bands from the optical, V, V, R, I, to the infrared, near infrared, J and H. What you'll notice is that all of the optical bands are strongly correlated. Measuring supernovae in the optical, all of the luminosities are correlated with them, so you don't really gain much in terms of new information by measuring them in different colors, except for the corrections terms, of course. But look at what happens here. When you look at the colors, when you look at the correlation between the optical band and the near infrared band, those correlations are almost zero. which is telling you that if you measure supernovae in the near infrared, you've got near infrared light curves of those supernovae, you're going to gain genuinely new information about them that's not contained in the optical light curve. And one of the reasons is because in infrared light, supernovae are less absorbed than in optical light. So you can see that here for one specific object, this posterior distribution for the distance modulus of that object versus its extinction. And so you can see here that the distance modulus determination is fairly uncertain. If you use only two optical bands, B and V, it becomes better if you include R and I information, and it becomes much better. It's vastly improved once you include infrared information, J and H bands. And so they are carrying out this program of using highly sophisticated, by using optical level models to analyze optical light curves and near infrared light curves of supernovae. And myself, my group, David Van Dyke here at Imperial College and others, we are thinking of expanding this approach to a full, complete vertical model. I don't want to go through any of this. I just want to flash it just to give a sense for how we can fully model the entirety of this problem using highly sophisticated statistical and sampling techniques. I didn't have time to tell you about the sampling techniques, importantly deep sampling, that can be used to then sample over this high dimensional parameter space. In our case, because all of these latent variables, we end up sampling on a parameter space that's got a dimensionality of a few thousand. In case of the Bell et al. Work, they sample over 50,000 plus parameters. So you need MCMC techniques that are adequate for the results. But that's a technical subject that I'll leave for you to explore in the references. Okay, so that's my overview and crash course on supernova type 1a Bayesian cosmology. What I want to do after the break is to move on to discuss Bayesian model selection and principled applications of that in cosmology. If there's any questions, as usual, please let me know. And also, if there's any follow-up questions via email, again, please do. I think it's time now to have a half an hour break, Andres, if you agree. Very good. Okay, very good. I'll see you in a bit.